Hello everyone! You have just seen a real-time demonstration of a dead reckoning algorithm for tracking robot position and orientation in 2D plane. The implementation is performed in a robot operating system and Rviz visualization software. In this tutorial, we explain how to implement the dead reckoning algorithm from scratch in the robot operating system. This tutorial is based on the Noetic Robot Operating System and the Linux version Ubuntu 20.04. However, everything explained in this tutorial can be generalized to other ROS version. This tutorial is based on the ROS serial Arduino library that is used to establish an interface between Arduino and the computer running ROS. Before watching this video tutorial, it's a good idea to go over my previous tutorial on how to establish a ROS Arduino interface and how to run ROS on Arduino. Also, a good idea is to go over this tutorial that I created that explains the dead reckoning algorithm. Links to these two tutorials, as well as to all the codes explained in this video tutorial, will be given in the description below this video. Here's the block diagram of our system. This is a differential drive robot. The differential drive robot consists of two wheels that are driven by two motors. To every wheel, we have attached an encoder that measures the angle of rotation of the wheel. Right and left motors are controlled by the PWM control signals. PWM stands for the pulse width modulation. The PWM signals are generated by the motor driver, and the motor driver receives the control actions for the left motor and for the right motor from our Arduino Mega. We are running Arduino Mega together with ROS serial Arduino library. At the same time, Arduino Mega receives left encoder readings and the right encoder readings. ROS serial Arduino library is used to communicate encoder readings to our computer and to receive motor command velocities from our computer. This is done by using this Bluetooth module with the product number HC06. I made a separate video tutorial explaining how to use this Bluetooth module. The communication between our Arduino and PC computer is performed by using several topics. For the motor control, we are using the left motor velocity topic and right motor velocity topic. On the other hand, to receive encoder readings, we are using the left encoder pulses topic and the right encoder pulses topic. On the other side, we have a PC computer with ROS. Okay, let's start with the coding and with the ROS implementation. First, we have to make sure that we have the correct Linux and ROS distributions. To check the current Linux distribution, open a terminal. And in the terminal window, let me just expand it. You can check the current distribution by running this command. Here it is. And as the output, you should see Ubuntu and you should see this version. This is very important. If you don't have this version of Linux Ubuntu, please install it. Otherwise, everything that I will explain in this video tutorial will not work. Of course, you can generalize everything I will explain with several modifications to other Linux distributions and to other ROS distributions. However, for the time being, let's stick to this distribution. The next step is to check our current ROS distribution. To do that, we need to execute the echo command. And as the output, you should see Noetic. Again, everything explained in this tutorial is applicable only to Noetic. If you want to use this code in some other distribution, you need to make a few changes. The next step is to create and upload the Arduino code. Let's start with Arduino coding. For that purpose, open Arduino. I made a tutorial explaining how to install Arduino in Linux, and you can find this tutorial on my YouTube channel. Over here, I will click on Not Now, and let's explain the code. So what is the purpose of this code? Number one, this code will receive control actions from a computer running ROS. We will receive desired velocity commands for our left and right motors. Let's bring up the block diagram once more. Here it is. We are now currently coding this block over here. Again, this Arduino should actually receive from computer motor velocities. Okay, what's the second purpose of the code? Let's see. The code should send back encoder pulses. We send back detected encoder pulses for left and right encoders. Let's look at the block diagram. Here they are. Here are the encoder readings. So what will happen over here? Arduino will receive left and right encoder readings. It will process them and it will send them back through this Bluetooth module to our PC computer with ROS. The topics for communications are left encoder pulses and the right encoder pulses. Okay, at the same time, this Arduino over here should receive the motor velocity, again by using a Bluetooth module, and the topics are left motor velocity and the right motor velocity. Then Arduino should process this and send control actions for left motor control and right motor control to the motor driver. All the processing and communication is actually performed by using ROS Serial Arduino library. I created a tutorial how to install and use ROS Serial Arduino library. Okay, let's go back to the Arduino code. The first step is to include ros.h. This is our Arduino ROS library for establishing communication and for running ROS nodes on Arduino. Then we will include this standard header file for sending and receiving messages of int32. This is basically a data type, and note that this is actually a ROS standard message. Okay, over here we define Arduino pins. We define the encoder pin left, encoder pin right. These are the pins for the left, right encoder. Then we define the right and left motor pins. You can see them over here. Then over here, we define other global variables and global objects. We define this variable for counting total pulses on our left encoder and total pulses on the right encoder. Note over here that for simplicity, we are using encoders that can only measure direction, actually can only measure the wheel rotation in one direction. Actually, they can measure both directions, however, they only produce pulses that are incrementally increasing, so they cannot detect direction. Next, we define two variables for motor velocities. These variables are actually set by ROS, that is, they're set by our PC computer. We have motor velocity left for the left motor and the motor velocity right for the right motor. These variables go from 0 to 255. Let's write this. Okay. Next, we need to define the ROS variable. This is the handle for the ROS node over here. And this is the callback function for the left motor. It simply sets the velocity of the motor on the basis of the received ROS messages. Let's see this function. It's void, name of the function, type of the message, int32, motor velocity left ROS, and over here we simply say that motor velocity left is equal to motor velocity left ROS.data. That is, we simply set the motor velocity on the basis of the message that's being received from our computer. And this is the message, motor velocity left ROS. Here is the same or equivalent callback function for the right motor. Here it is. It simply sets the velocity of the right motor on the basis of the received ROS message. The received ROS message is motor velocity right ROS, and .data we use to receive the data, and we set the motor velocity right. That is, in this way, on the basis of communicated messages, we control motors. Here are the publishers for the encoder pulses. This is our left encoder publisher. The message will be int32. And here it is. Here's the function. And here's the right encoder publisher. This is the variable. And here is the function. Over here, it's very important to properly specify the topics. We have the topics left encoder pulses and right encoder pulses. Here they are, left encoder pulses and right encoder pulses. And these topics should perfectly match the topics defined on our computer. And we will go back, actually we will explain the code implemented in our computer later on. But keep in mind, again, that these names should match the names in the functions on our computer. So what are these two functions? These two functions are used to simply publish the messages. Okay, then we need to define the subscribers for the left and right motor velocities. Here are the functions. Again, these two topics have to perfectly match the topics on our computer. And let's look at the block diagram. Here's the topic left motor velocity, and here's the topic right motor velocity. Here the function specify the name of the topic, and the callback function motor left and the callback function motor right. These two functions are actually given over here. Callback function motor left and callback function motor right. Okay, let's continue. Here's our setup function. We set up the encoder pins. Here they are. We attach the interrupts for tracking the pulses. Namely, this is a standard approach for tracking the pulses on the encoder. Then we specify the pin for the left motor, we specify the pin for the right motor, and initially we will set all the motors to off. Digital write input 1, input 2 for the first motor, low, and digital write input 3, input 4 for the right motor to be low. That is, we turn off the motors because we don't want initially motors to spin. Next, let's set up the ROS functions and other things. Over here we specify the baud rate. This baud rate is the baud rate of communicating messages between Arduino, or better to say ROS serial library, and our computer. And this baud rate should perfectly match the baud rate specified in our launch file on our computer. We will come back to this later on. Here we will initialize the ROS node, and we set the publishers and we set the subscribers. Here is our loop function. Over here we spin our node. Then we set the speed of the motors on the basis of received values. The motors is controlled, or actually better to say, both motors are controlled by using the PWM or pulse width modulation signals. We control the motors by sending variables from 0 to 255, or better to say integers from 0 to 255 to the motor driver, and the motor driver performs all the magic. Here we write the messages to our two motors on the basis of the received variables from our computer, and motor velocity left and motor velocity right are sent from the computer. Then over here we set the direction of the motor and we turn them on. Over here I'm simply specifying one direction. However, you can also play with the direction, and you can also encode communication about direction. However, here I'm simply specifying, or better to say sending, from my computer velocities only in a single direction. Then, again, we need to spin our ROS node. We spin it once more. Note that we spin it over here, and we repeat the spin operation over here, and we send back the encoder readings. We fill in this message left encoder ROS.data and right encoder ROS.data with total pulses left, total pulses right. These are the variables tracking the number of pulses from our encoder, and we simply publish them over here. And we spin again our ROS serial node, and we delay for 20 milliseconds. Here are the two interrupt functions. Here is the interrupt function for the left encoder, namely whenever the rising edge is detected, we simply increment the readings, or better to say the variable storing the total pulses of the left encoder. Similarly for the right encoder, here is the interrupt function. When the rising edge is detected, we simply increment the total pulses on the right encoder, or better to say this variable storing the total pulses on the right encoder, and that's it. This is our Arduino code. Here's the code again. Line 0 to 31, then 31 to 61, then 61 to 91, then 91 to 121, then 121 to 151, and finally 151 to 180, and then we have from 180 to 197. That's it. The next step is to upload the Arduino code. However, when uploading the Arduino code, you need to disconnect the pins 0 and 1 of the HC06 Bluetooth device. This is very important. These are 0RX and 1TX pins, and they should be disconnected when uploading the code through serial port. Otherwise, if you don't do it, you will not be able to upload the code. Again, you need to disconnect the pins of HC06, pins 0 and 1, before you can upload the code. Once you do that, you can simply make sure that the proper port is selected over here, that the proper board is selected over here, and you can simply verify the code clicking over here and upload the code over here. That's it. The next step is to create a Bluetooth connection between the computer and Arduino. Let's do that. In Linux, click over here, then search for Bluetooth. Here it is. Here's our device. This device, called HC06, is connected to our robot and our Arduino. Double-click on this device and wait over here. It will take some time to set up the device. After some time, you will see this window where you need to confirm Bluetooth pin. In my case, the pin is 1234. However, the pin can also be 000, so check both options and click on confirm. And then after some time, you should see that it's connected, and again you will see disconnected. Don't worry about that, since we will manually connect to the device from a Linux terminal. But it's very important that initially you saw connected. And if you see disconnected, that's fine. Okay, let's continue. Before closing this Bluetooth window, double-click over here and memorize this address. Simply copy and paste it or write it on a piece of paper. We will need this address later on. Next, let's test the Bluetooth connection. To test the Bluetooth connection, let's copy this command over here and let's go to the terminal. Let's open a new terminal and let's test the connection. We are running sudo rfcomm connect. We specified the communication port, we specified the address, and let's see what will happen. Enter the password and wait. Then after some time, if you have properly set up everything, you should see this message connected to this device, and here's the address on channel 1. That's it. Let's press Ctrl C to hang up, and let's continue with creation of our package. The next step is to create a workspace and package. For that purpose, let's run this command. This command will create the folder called ROS_dr_ws. This is our workspace folder, and inside of that folder we will create our source folder. Okay, let's navigate to our workspace folder by running this. Then let's run catkin make. Okay, then let's source our environment. And then let's create our catkin package. To create the catkin package, let's move to the source folder. And inside of this source folder, we need to execute this command. The command is catkin create package. ROS underscore dr underscore package is our package name. That is, this is the package name. And the package depends on these built-in ROS2 packages. That is, these are the dependencies. They are geometry messages package, standard messages, navigation messages, TF2, robot state publisher, Rviz, ROS-PY, and ROS-CPP. Let's execute this command. And here it is. Okay, it's always a good idea to learn more about these packages. Here are the links that you need to follow in order to learn more about these packages. However, for the time being, I don't have time to explain all the details about these packages. The next step is to create publisher and subscriber files. To do that, we need to navigate to this folder. And in this folder, we need to create our publisher Arduino. Let's do that. Here it is. I'm using gedit. And over here, we need to type our publisher node. To make this tutorial as short as possible, I simply copy and pasted the content of the publisher file. Here's the main idea of this publisher file. This publisher file will actually publish messages from 0 to 255. These messages will be used to control left and right motors. Left motor velocity is the topic for sending control actions to the left motor, and right motor velocity is the topic for sending messages, or better to say control actions, to the right motor. On the other side, we will have Arduino that accepts messages through these topics and distributes these messages to the left and right motor. Okay, every file should start with this line. This is the standard line. Then we need to import ROS-PY, and then since we are sending int32 messages from 0 to 255, from std messages.message we import int32. This is our node name. It's called message publisher. And these are the topic names. Here you have to make sure that in Arduino code the subscriber nodes are subscribed to these exact topics. They are left motor velocity, right motor velocity. Here we initialize our subscriber node. We set anonymous to true to make sure that the node has a unique name. Actually, here I made an error. This should be a publisher node. Okay, let me correct this. This parameter will add random numbers to the end of the node name. So you run this command, ros.init node, you specify the node name that we define over here, and anonymous true. Over here, we are saying that our node is publishing messages to the specific topic names. We specify the type of the message we want to publish. They are int32. We specify the buffer size. This simply means that we limit the number of buffered messages if the subscriber cannot receive the messages fast enough. So what's happening over here? This is the publisher left motor. We call ROS-PY.publisher. We specify topic name left motor. We specify the type of the message, and we specify the buffer size. We do the same thing for the publisher right motor. We specify the topic name right motor, type of the message, and the buffer size. Over here, we specify the frequency of publishing the messages. We will publish the messages with the frequency of 1 Hz. However, later on, I will modify this communication such that I'm submitting messages and then I'm waiting until new messages are being sent by the user. Here we initialize the integers that we will plan to send. For the left motor, we specify 0, and for the right motor, we specify 0. And over here is the main while loop. While not ROS-PI is shut down, we execute ROS-PI loginfo left motor, right motor. Loginfo is simply used to display messages on the computer screen. Over here, we read the input from the user. We are plotting, or better to say printing, on the computer screen. Enter left motor velocity, enter right motor velocity. We read these values, and we simply publish these values to the appropriate topics, and we sleep. That is, we pause the previously defined rate. And that's it. Simple as that. Nothing special. Here again is the file until the line 35, and here's the end of the file. Let's save this file and let's close it. Next, we need to define the subscriber file. Save the previous file, close the editor, and let's create the subscriber file. And over here, I will actually use another software to explain this file. Namely, I will use Anaconda Spider. I'm using Anaconda Spider since gedit cannot sometimes properly display tabs, and it's a better idea to use some editor for more complex Python files. Here, I open the subscriber file in Spider Editor, and I simply copy and pasted the content of the file. Okay, so let's explain this file. The idea of this file is actually to implement the dead reckoning. This is the subscriber node that receives encoder readings from Arduino and calculates position X and Y of the center of the robot, as well as the robot orientation angle. That's usually denoted by theta. These values are calculated from the encoder readings by first calculating the velocity and then X, Y, and theta. That is, this code performs that reckoning. After calculating X, Y, and theta, we create a quaternion and create an Odometry ROS object. This is very important because we need to create an Odometry ROS object to communicate the position and angular orientation such that we can display the results in Rviz. Okay, so let's start with the explanation. First of all, we need to import ROS-PI, and since we are expecting to receive int32 messages from the left and right encoders, we need to import from std messages.message int32. Then this is our odometry, and we need to import the odometry. Then we need quaternions over here, and over here we need transform broadcaster from TF broadcaster, and we need the standard Python imports from add, import cos, sine, and pi. Okay, here's the class that implements that reckoning. Here's our constructor. This is the node name. Note here that ROS might add a random number at the end of this node. Then, these are the topic names. Again, these topic names, that is, this left encoder pulses and right encoder pulses, should match the topic names in Arduino code. These are the frame names for broadcasting odometry. They are base frame ID, base frame. We are actually getting the parameters over here. Odom frame name, odom frame. And we store the values in base frame name, odom frame name. Over here we need to define the geometry of our robot. This is the wheel radius, and this is the distance between the wheel. And over here we're specifying our encoder properties. We are using the LM393 encoder, and we need to specify encoder pulses constant. In our case it's 20. And this is the update frequency for publishing odometry in Hertz. I'm specifying over 10 Hertz. However, you can also change the value. You can go with 50 Hertz or 30 Hertz. And this is the flag for initial reading. These variables are set to 0 after the first reading from the encoder topics. Then we have these two variables. These variables are used to store the initial readings from the encoder topics. Namely, when you start the system, you might have non-zero encoder readings, and we need to store these readings in these variables. Here, they are initialized by zeros, however, they are updated in the first encoder reading. And then we specify left encoder reading at the current time step k, current value left encoder is 0, and the previous time step k-1 past value left encoder. So we will store current value and past value, and we will update the past value by the current value. And here the right encoder readings, they are current value right encoder and past value right encoder. Then we specify the time, we specify current time left encoder and current time right encoder. Then we specify current and past time for the complete code, and we specify the past time. Over here we specify the kinematic states. They are x, y, these are the coordinates of the center of the robot, and we have the orientation angle theta, and that's it. Over here we need to start a node. We initialized our node. We set anonymous to true to make sure that the node has a unique name. And this parameter will actually add random numbers to the end of the node name. This is not very important. Over here we get the past time, we update the node name, and we print the message. The node number of the node, or the name and number, has started. And we end this code block. Over here we set subscribers and publishers. We say subscribe to the messages from the left encoder, rospy.subscriber, we specify the topic name, we specify the type of the message, and we specify the callback function that will be defined later on. We do the same thing for the right encoder. And over here we publish an odometry. Self.odometry publisher is rospy publisher odometry, odometry, and the buffer size. And over here we publish the transform broadcaster. Okay, this is the end of the constructor function. Here are the callback functions. These are the callback functions that are called when the messages are received. This function will print the encoder readings to the screen. Note that these functions are running in the background by the ROS system. By the way, over here I commented the printing part. However, you can uncomment this to basically make a code easier to debug. So what's happening over here? If the message is received, if this happened initially, we do this, we basically initial value left encoder is message1 data, and we set this flag to 0. Then, after the initial time, we simply do this, message1.data minus self.initial value left encoder to get actually the relative encoder reading, and we say self current time left encoder is rospy get time to get the time of the particular reading. We do the same for the right encoder. So these two code blocks, or better to say these two functions, are equivalent. One is written for the left encoder and one is written for the right encoder. These functions are actually callback functions that are called in the background. This is our update function, and this is the main function in our code. Over here we get the current time, and if the current time is larger than the past time, we calculate the time step. The time step is current time minus past time. Over here we calculate left and right encoder angle changes. We simply convert the pulses to readings. We have left encoder angle change and the right encoder angle change. Then over here we calculate left and right encoder angular velocities. We simply divide the angle change by delta t. This is very important since we are calculating angular velocity. We do that for the left encoder, for the right encoder. And over here we calculate left and right wheel velocities. We simply multiply the radius by the left wheel angular velocity to get the left wheel velocity. And we do the same to calculate right wheel velocity. Over here we calculate the velocity of the robot center. The velocity is left wheel velocity plus right wheel velocity. Now, if you wonder from where I got these formulas, well, you need to read my first tutorial. And let me show you how to find that tutorial. So click over here, I will click over here, and then I will go all the way at the top of my manual, and you need to go over this tutorial. Actually, this tutorial is already open over here. Here it is. You need to read this. What is dead reckoning? And if you scroll all the way down, down, you will see the main equations I'm implementing. Here are the few main equations. Also, there is another tutorial that is relevant for you, and you should also go over that tutorial. Here's the second tutorial that you need to go over in order to understand the kinematics of differential drive robot. I will provide a link to this tutorial in the description below. Let's go back to the code. So we stopped over here. Next, we need to calculate the angular velocity of the center of the robot. Here it is. And over here, we need to implement the dead reckoning equations. First of all, we calculate the distance traveled as velocity times the time instant. Then we calculate the angle change as the angular velocity times the change in time. And over here, we implement the dead reckoning equation. So if I go back to my original code, let me just see, or better to say to the original tutorial. Let me close this one and let me show you what are the equations. So here are the dead reckoning equations. This set of equation, or you can write these equations like this. And this is exactly what is implemented over here. You can see that x is the previous value of x plus the distance traveled times the cosine. Y is previous value of y plus the distance traveled times sine, and theta is the previous value of theta times the angle change. And these are the precise equations given over here. Okay, let's continue. Here we print the results for inspection, and here's a very important part. Over here we need to define a quaternion. Quaternion is a geometrical in kinematics object that's very important in robotics and aerospace. We basically encode the orientation of the robot by using quaternions. We call the constructor for the quaternion to create the object, and here is another one. Then we specify x, y, and z values. They're pretty much standardly defined. You just need to implement the formula, and we specify and define quaternion tuple. Quaternion 1.x, quaternion 1.y, quaternion 1.z, and quaternion 1.w. Over here we publish the odometry, and we continue. We define odometry 1 object, we specify the header stamp, we specify the header frame ID, we specify pose.position x, position y, position z, we specify the orientation to be equal to quaternion 1, we specify the child frame ID. This is very important. The child frame for our odometry is base frame, and base frame name is very important and it should be defined. So if you now go over here and if you search base frame name, you will see it over here, base frame. And this is very important because this base frame should correspond to base frame in our URDF file. We will explain this later on. Then we specify velocity. For the linear, x is simply velocity because x is in direction of the rotated body frame, y 0, and over here we have angular velocity for z. And we call odometry publisher.publish, and we publish odometry 1. And over here we update the time, so the past time is actually the current time, past value left encoder is the current value left encoder, and past value right encoder is the current value right encoder. And that's it. Simple as that. Next, make sure to save this file, then close Spider or the editor, and let's go to our original terminal. Again, over here I need to close my gedit file. I can simply basically go to my original folder and I can type lsl and I can see publisher and subscriber Python files. This is very important. Okay, let's continue. So the next step is to set the execution rights such that we can execute publisher and subscriber nodes. So let's learn how to do that. Let me just scroll all the way down. Let me move this a little bit, perfect like this. So to set all the executable permissions, you need to change these parameters over here. Over here we can see that we cannot execute both of these files. So let's run this command to set the executables. Here it is. Let's run this to see, and we can see that we can execute these files. The next step is to create a launch file. First of all, let's navigate to this folder. Then in this folder, let's create our launch folder. Here it is. Then let's create the launch file by first navigating to this launch folder. And in this launch folder, let's create the launch, oops, I made an error here. Let's create the launch file. Here it is. And over here again, I will copy and paste the content of the launch. Here's our launch file. Here we begin the launch file, here we end the launch file. Here's the name model. We use the parameters, use graphics user interface, values yes. Over here we specify the Zacro or URDF files that define the robot geometry. The name is robot description, and define the Zacro in order, find ROS DR packages URDF, and this will be the name of the URDF, or better to say Zacro file defining the robot geometry. Note that we still didn't create the URDF folder. We will create it after creating the launch file. However, you can already specify this name. Here we start the robot state publish, which will publish TF. Robot state publisher, and type robot state publisher. Over here we launch visualization in Rviz. Node name is Rviz, package is Rviz, type is Rviz, and over here we specify the configuration file. Note that the configuration file will be stored in URDF folder and currently doesn't exist. We will create our configuration file the first time we actually run our model in Rviz, and then we will save the configuration. Over here, it's very important to run the ROS serial driver for handling Bluetooth serial port. The node name is robotbt driver node. The package is ROS serial Python. Here is the file, serial node Python, and here are the arguments. Note here that we are specifying the baud rate, and this baud rate should match the Arduino baud rate, and this is the port. This port is used in establishing communication with Bluetooth device. And we end the node, and then we have the node package, ROS drive package, and this is our main part. Subscriber Arduino Pi, name Odometry, and output should be screen. That's it. Let's save this file. Let's close this and let's continue. The next step is to create the URDF file. That is, we need to create the robot geometric description. For that purpose, again, let's change the name or our current location, and let's create the URDF folder. Here it is. Inside of that folder, we will create the URDF file. First, let's navigate to the URDF folder, and this URDF folder, let's create the URDF file. The URDF file will be called robot_model Zacro. However, this is still a URDF file, and here it is. Again, I will simply copy and paste the content of the Zacro or the URDF file in interest of brevity. Here is the complete URDF file. First of all, we start with this line. Over here we create the robot tag and we end robot. This is very important. That is, this is the end and this is the beginning. We specify the robot name, and this part is standard. Then we specify the robot geometry parameters. We have X, Y, and Z dimensions of the robot base. Here are the values. Then we specify the wheel geometry. We have the wheel link radius, the wheel link length, and wheel link x location. And this is the sphere that acts like as a caster. That is, we have two wheels with this geometry, and we have the third support wheel, or in our case, for simplicity, we simply use a sphere. Here's the sphere radius, sphere joint y direction, and z-sphere. These are the offsets and some other parameters. Over here we define the constants, we define the pi constant and half pi. Then we define the material colors. Here they are: white, yellow, green, and red. Some of these material colors we don't use. Next, let's start with the definitions. First of all, we define the base frame, or basically the base link. We start link, we end the link, and it's simply base frame. Then we define the first joint. This will be our base joint. It's fixed. We specify the origin, x, y, z, and roll pitch yaw rotations. And over here, this angle for yaw rotation is in radians, and it's half pi. Then we specify the parent link, we specify the child link, and that's our first joint. Here's our base link. This is geometry. It's a box with body link x dimension, body link y dimension, and body link z dimension. And we specify the origin and then visuals. Then we define the joint name. This is the left wheel joint. Type is fixed. We specify x, y, z, and roll pitch yaw. These are the orientation of the center. We specify the parent link. It's a base link. The child link will be left wheel link. The axis of rotation is x, and we specify the standard things such as limit, effort, and velocity. And we specify damping and friction. Next, we define left wheel link. We specify the origin, we specify the geometry, we specify material, and that's it. Next, we define the right wheel link. We specify the origin, geometry over here. It's the cylinder, radius and length, material, and next we specify right wheel joint. It's fixed joint. We specify the origin, the parent link, the child link, the axis, and that's our joint. Next we define our robot caster joint. This will be a simple sphere. It's fixed. We specify the parent link, we specify the child link, we specify the origin. And finally we define the robot caster backlink. We specify the origin, we specify the geometry, sphere, it's simple sphere, we specify material color, we end the visual, we end link, and that's it. Here again is our URDF file from line 1 to 35, then from line 35 to 67, then from the line 67 until 98, then from the line 98 to the end, and that's it. Don't forget to save this file and close it. Let's continue. Next, let's initialize the Bluetooth connection from a Linux terminal once more. Open a new terminal, and under the assumption that everything is connected, and let's verify that, click over here, search for Bluetooth, and you can see device over here. Never mind, it's disconnected. This is still okay. Then over here, let's simply establish the connection once more. Enter your password and wait over here until the communication is established. We are currently connected, and now we can launch our file. That is, we can launch the launch file. For that purpose, open a new terminal, and first of all you need to run the ROS core. Here it is. Okay, now the ROS core is running and we can continue. Next, open a new terminal. Then, in that terminal, you need to source the environment. That is, you need to source the newly created package. And then let's continue. We can simply run our launch file. Here it is. Okay, now you can see over here that nothing is happening. However, you can see a very important thing. You can see the time difference and x, y, and theta. So what's happening behind the scene? We are running actually the the subscriber node on our computer. That is, the subscriber node is currently running. It receives messages, or better to say encoder readings, from our robot, that is, from the ROS serial library running on robot. And the communication is established. You can see the orientation, the position and the orientation of the robot. Now, if you try to move the robot, you should see, as I see it over here, that X, Y, and theta are changing. This means that the communication is properly established and that we can get the encoder readings and we can perform that reckoning. However, we don't see anything over here. Why is that? Well, because we are not currently displaying anything in Rviz. To display our robot in Rviz, we need to do a few things. First of all, over here as a fixed frame, we need to specify odometry frame. Then we need to add actually our robot. We do that, let me just do that. We click on add and we search over here for robot model. And here it is. And then you will see the robot model. Here it is. Now, if you try to move the robot, you can see over here that the robot is actually moving. This is very important. However, what I like to do, and this is what I suggest you to do, is actually to do a few more adjustments. Over here, click on add and click on TF. And you see all the possible frames you have. Now, over here under TF, you can make a few adjustments. So you click on frames and deselect this one, and then let's just show the base frame. And here it is. And now we are showing the base frame, and you can see as you move robot, you can see how the base frame change, and you can see its connection with respect to the 0 over here. This arrow is actually the vector connecting the base frame to 0. This is very important. Now, every time you run a launch file, you will have to do these adjustments. However, that's not a good idea. Well, a better thing is to save this configuration. Let's learn how to save this configuration. To save the configuration, click on File, Save Config As, and let's find the correct folder. So where is our folder? You need to find the home folder, and inside of the home folder, you need to find our package. Let's see where it is. Here's the workspace, source, drive package, source. It's actually not here. It's in URDF. And over here, the name of the file is config.rviz. Now, let's close Rviz. Let's go back to this window. And let's try to run again our launch file. We run ROS launch, ROS drive package, launch file. And let's wait a little bit, and voila, here it is. Now you can see your complete robot, and you can see if you move robot, you can see that it's actually moving with all the frames and everything working perfectly. Okay, and finally, let's learn how to run the publisher node. The publisher node will simply publish motor commands, and let's learn how to do that. This is actually the last thing that we need to do. Well, again, to run anything in ROS, open a new window, source the environment, and after sourcing the environment, simply run the publisher file. And over here, you'll be asked several things. You will be asked two things. You will need to specify the left motor velocity, let's do 200, and let's specify the right motor velocity 0. And if you do that, you will see that the motor is actually spinning. You can hear it in the background that my motor is spinning. And let me turn off the motor so I can continue to speak. And that's all. Thank you very much for your attention.